Alrighty, excuse me. We're going to go ahead. So we filled this part of the blank paper up. We're going to go to task number 3. We're going to fill in what those folks were having to do with their task. So let's go to task number 3. So task number 3. People that had task number 3, they were looking at a pattern, I guess, geometrically, and numerically, I should say both, because they were building this triangle that started with these 6 numbers. And they were told that they can continue the pattern and build a triangle by adding 2 numbers that are next to each other and then writing them right under the 2 numbers that you added. So, for example, if I add 1 and 2, my answer is 3. I'm going to write it right under and in between those 2. Or, if I add 2 and 1, well, that number would be 3 again. But when I get over here, notice this doesn't create a triangle. It almost seems like I need a number over here and a number over here, and that would create the triangle. And so therefore, if you have nothing plus 0, nothing plus 1, then that gets you 1. And if you have nothing plus 1, well, that gets you 1. And in doing so, now I have a triangle. Also, notice the sides of the triangle this way and this way are all in a row of 1s. Okay, well, let's keep going. If I add 1 and 3, you get 4. If I add 3 and 3, you get 6. You're just adding the numbers next to each other, and you're writing the answer under them right in between. But again, I'm missing the ends. If I think of it as 0 plus 1, well, that would be 1. And if I think of 0 plus 1, that would be 1. And once again, my beginning and end are always 1. That's always going to be true, by the way, that the beginning of the row and the end of the row are always going to start and end with 1. All right, we'll do one more, and then we can look for some patterns. So 1 and 4 gives me 5, and then 10, 10, 5, 1, and 1. How am I getting these yellow numbers? I'm just adding the numbers above them and then writing the answer right under. Do you recognize this triangle? Maybe you've studied it in another math class. This is called Pascal's triangle. Pascal's triangle is named after Blaise Pascal, who was a French mathematician who did a lot of work with, developing the ideas behind computers. But in this case, he comes up with this pattern that the numbers actually mean something. Now, you might think this is something an elementary school student can do. Yes, and it turns out that the numbers that we're getting here actually signify something important. I'm going to do one more row, and then I'm going to stop. So this will be 1 and 5, that's 6. This will be 15. This will be 20. This will be 15. This will be 6. And then I end with a 1, and I start with the 1. So I still have this triangle, right? Wink, wink, wink. There's my triangle. And by the way, this is a 15, in case you were wondering. 15. And this is a 15 as well. All right. So just so you know, every row I try to do in a different, every new row that we did, I try to do in a new color. And every row has a designated number. And we don't start with 0. We don't start with 1. We actually start with 0. This would be the first row. And then this is the second, and the third, and the fourth, and the fifth, and the sixth. Now, if you notice, let me try to choose a color that stands out. The second row, the second number is 2. The third row, the third number is 3. So this is one way you can tell which row am I looking at. With a 6th row, that would be this one, right? Cool. So one of the things that these people noticed that were doing this task was when you look at the rows, there's a symmetry to the numbers, right? If you look at each row, this and this are the same value, and this are the same value, and this are the same value. The only reason 20 doesn't have a partner is because we have an odd number of values. But if I go up to the next line, 1 and 1, First one from the end, first one from the beginning is 1. Second one from the beginning, second one from the end, they're both 5. They're the same. So if you can figure out the first 3, the last 3 are the same, but in reverse, right? There's a symmetry in the numbers for every row. So that's kind of important. That's going to come back to help us. But I'm going to stop here in terms of the triangle, Pascal's triangle, and say Pascal's triangle, not a difficult thing to create. Like you can get a scratch sheet of paper and make this triangle or go as far as you want, right? Like you can go 1, 7, 21, 35, 40, 35, sorry, 35 repeats, 21, 7, and 1. And I can continue to get more and more rows. What's going to be interesting and why we're even studying this pattern is because these numbers represent something. Now, if I box the 4th row, and you know this is the 4th row because the second number is a 4, I've seen those numbers before. If I go back to task number 2, those are the same numbers that folks got when they were counting the different ways a heads could appear in a coin flip with 4 coins. It is the same set of numbers, 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. Is that coincidence? Well, no, it's not coincidence at all. It turns out Pascal's triangle, even though it's really easy and simple to create, gives us some rich information and important information about the number of combinations we can make. The number of combinations of flipping 4 coins where one of them is heads, or 3 of them are heads, or 4 of them are heads. That's what the connection is between Pascal's triangle, which again seems pretty easy to do, and flipping coins and looking at the combinations of outcomes that we can get. People that did task 3, this is where they stopped. They also did another little experiment and noticed that when you add these two numbers, when you add the numbers in every row, I should say, 2, if you add these, 4, if you add the ones in green, 8, if you add the ones in purple, 16, what's happening to the numbers here? Every time I go down the row, another row, the sum of the numbers in that row, the sum doubles, 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 doubles. Now that has something to do with something I mentioned over here, which is if you increase the number of coins, the number of ways increases by doubling as well. Is it the same number? 5 coins, 32 ways. Row number 5, the sum is 32. We're going to come back to this idea, but again, this whole unit has been about finding patterns. All we're doing here is looking at patterns.